Welcome back to Pentagram Prime, everyone. Today we will be completing exercise 8.b on page 302 of Basic Complex Analysis, 3rd edition by Marsden and Hoffman. We will be showing that the integral of e to the negative x divided by 1 plus e to the negative 2 pi x from minus 2 plus infinity is equal to the reciprocal of 2 sine 1/2. We will, of course, be doing this by expanding the problem into the complex plane. To that end, we will choose a path of integration forming a rectangle with vertices little r0, little r1, negative little r1, and negative little r0, referring to the real and imaginary components of z respectively. We will also delineate the segments as capital I sub 1 for the bottom, capital I sub 2 for the right-hand side, capital I sub 3 for the top, and capital I sub 4 to describe the left-hand side. These sides form a closed loop that allows us to exploit residue theorem. We will refer to the aforementioned contour integral as I sub L, where L stands for loop, and where z is equal to x plus iy. I sub L is equal to the sum of the 4 individual path integrals, and we will denote them as capital I sub Roman numeral 1 for the bottom, capital I sub Roman numeral 2 for the right side, capital I sub Roman numeral 3 for the top, and finally capital I sub Roman numeral 4 to describe the path integral on the left side. The numerator is defined for all values of z, so it falls upon us to look for some zeros in the denominator. Setting 1 plus e to the negative 2 pi z equal to 0, we find that the exponent must be equal to plus or minus pi I. This gives us plus and minus I over 2 for zeros in the denominator of the integrand. As you can see, positive I over 2 lies inside of the contour integral and is thus the only singularity that we will be focused on. Referring to the integrand of capital I sub L as f of z, we can now separate the numerator and denominator into separate functions. F of z becomes g of z divided by h of z. Evaluating the derivative of h prime at I over 2, we see that the result is a non-zero value. Similarly, g of I over 2 gives us a non-zero value, and along with a zero value for h at I over 2, we have satisfied the requirements for use of method 3 in table 411 on page 250 of the text. This allows us to calculate the residue at I over 2 utilizing g of z naught divided by h prime of z naught. In our case, z naught is plus I over 2, and the residue is equal to e to the negative I over 2 quantity divided by 2 pi. The contour integral, capital I sub L, equals 2 pi I times the aforementioned residue, and this works out to I times e to the negative I over 2. Thus, we can equate the sum of the 4 path integrals to I times e to the negative I over 2. Path integral capital I sub 1 takes us along the real axes from negative little r to positive little r. This gives us the following representation for capital I sub 1. We can ignore the 0i terms, of course, and the fact that little y is always 0 along this path means that we can equate both z and dz to x and dx respectively. This allows us to convert capital I sub 1 to that of an integral of x alone. If we take the limit of little r as it approaches infinity, we get the same integral that we are trying to solve. Path integral capital I sub 2 takes us from positive little r on the real axes up to a point in the first quadrant designated by positive little r plus I. Along this path, z is equal to positive little r plus iy, and taking the derivative of z gives us dz equal to I dy. Along this path, the only variable that changes is y, so we can reformulate the integral to that of a one-dimensional integral from 0 to 1. For our purposes, It helps if we separate the real and imaginary components in the integrand. Next, we consider the absolute value of the integrand. The absolute value of AB over C is equal to the absolute value of A times the absolute value of B divided by the absolute value of C. This allows us to separate the absolute value of the numerator from that of the denominator while splitting the numerator into a multiple of two separate absolute values. The absolute value of I is 1, so we can cross it out. Next, we use similar logic to separate the two exponential terms in the numerator into separate absolute values. The absolute value of e to the negative iy is equal to 1 for all real values of y, so we can cross it out, leaving us with e to the negative little r in the numerator. Next, we look closer at the denominator of the integrand in question. We begin by factoring a minus sign out of the second term. Then we consider something called the reverse triangle inequality. This allows us to say that the aforementioned denominator is less than or equal to the absolute value of the difference of the absolute values of the constituent terms. The minus sign inside of the second set of absolute values can be ignored. From here, the rules surrounding absolute values allow us to separate the two exponential terms into their own absolute values. Of those, the exponential on the right has the value of 1 for all y. All other terms within the outer absolute value signs have exclusively positive values, so we may remove the two remaining sets of inner absolute value signs. So by first factoring out a minus sign from the denominator of the absolute value of the integrand, then exploiting the reverse triangle inequality, and removing the absolute values within the right side of that inequality, we may state the following inequality.
What is it? What is it? It's not fair. Tell me.
I'm getting to that. Shut up. We will next take the reciprocal of both sides of the inequality, and whatever you do, don't forget to reverse the polarity. From here, we are welcome to multiply both sides of the absolute value of e to the negative r. This quantity is positive, so the inequality holds. On the left side of the inequality, rules regarding the quotient of two absolute values allows us to combine the terms into a single absolute value. What if we multiply both sides of the inequality by the absolute value of I times e to the negative iy? Positive quantity, since it is an absolute value, of course. Conveniently, it's also equal to 1, so we can ignore it on the right side of the inequality. On the left side, we can incorporate it into the original absolute value. From here, we can integrate both sides with respect to y for values from 0 to 1. Note the y dependence, or lack thereof, specific to the integrand on the right-hand side. This lack of y dependence means that we can completely excise the integrand from the integral itself. What remains of the integral with respect to y is equal to 1 minus 0 and ultimately disappears, leaving us with the integral on the left. From here, the integral inequality becomes important. For those of you new to my channel, the integral inequality states that the absolute value of an integral is less than or equal to the same integral with absolute value signs around the integrand. Applying this to the previous inequality, we see that the absolute value of the entire integral is less than or equal to the previous inequality's left side. Removing the centerpiece of the triple inequality in red ink, we can state that the absolute value of the entire integral is less than or equal to the aforementioned expression for little r alone. The integral inside of the absolute value signs on the left is the same as capital I sub Roman numeral 2, and I love it when an equation simplifies. Something elegant about it. From here, we consider the limit of the inequality as little r approaches infinity. Both the e to the negative little r and the e to the negative 2 pi little r terms go to 0, while the constant 1 remains 1. The result is that the right side of the inequality approaches 0 as little r approaches 0. Since an absolute value cannot have a negative value, we are free to change the inequality to that of an equal sign. And since an absolute value can only equal 0 when its argument is 0, we are free to remove the absolute value signs around capital I sub Roman numeral 2. Thus, the limit of capital I sub Roman numeral 2 as little r approaches infinity is 0.